In computability theory and computational complexity theory, a decision problem is a question in some formal system with a yes or no answer, depending on the values of some input parameters. Decision problems typically appear in mathematical questions of decidability, that is, the question of the existence of an effective method to determine the existence of some object or its membership in a set. Some of the most important problems in mathematics are undecidable. For example, the problem, given two numbers x and y, does x evenly divide y, is a decision problem. The answer can be either yes or no, and depends upon the values of x and y. A method for solving a decision problem, given in the form of an algorithm, is called a decision procedure for that problem. A decision procedure for the decision problem, given two numbers x and y, does x evenly divide y, would give the steps for determining whether x evenly divides y, given x and y. One such algorithm is long division, taught to many schoolchildren. If the remainder is 0, the answer produced is yes, otherwise it is no. A decision problem which can be solved by an algorithm, such as this example, is called decidable. The field of computational complexity categorizes decidable decision problems by how difficult they are to solve. Difficult, in this sense, is described in terms of the computational resources needed by the most efficient algorithm for a certain problem. The field of recursion theory, meanwhile, categorizes undecidable decision problems by Turing degree, which is a measure of the non-computability inherent in any solution. Decision problems are closely related to function problems, which can have answers that are more complex than a simple yes or no. A corresponding function problem is, given two numbers x and y, what is x divided by y? They are also related to optimization problems, which are concerned with finding the best answer to a particular problem. There are standard techniques for transforming function and optimization problems into decision problems, and vice versa, that do not significantly change the computational difficulty of these problems. For this reason, research in computability theory and complexity theory have typically focused on decision problems. Definition: a decision problem is any arbitrary yes or no question on an infinite set of inputs. Because of this, it is traditional to define the decision problem equivalently as the set of inputs for which the problem returns yes. These inputs can be natural numbers but may also be values of some other kind, such as strings over the binary alphabet 0, 1, or over some other finite set of symbols. The subset of strings for which the problem returns yes is a formal language, and often decision problems are defined in this way as formal languages. Alternatively, using an encoding such as Gödel numberings, any string can be encoded as a natural number, via which a decision problem can be defined as a subset of the natural numbers. Examples: a classic example of a decidable decision problem is the set of prime numbers. It is possible to effectively decide whether a given natural number is prime by testing every possible non-trivial factor. Although much more efficient methods of primality testing are known, the existence of any effective method is enough to establish decidability. Decidability. A decision problem A is called decidable or effectively solvable if A is a recursive set. A problem is called partially decidable, semi-decidable, solvable, or provable if A is a recursively enumerable set. Problems that are not decidable are called undecidable. The halting problem is an important undecidable decision problem. For more examples, see List of undecidable problems. Complete problems. Decision problems can be ordered according to many reducibility and related feasible reductions such as polynomial time reductions. A decision problem P is said to be complete for a set of decision problems S if P is a member of S and every problem in S can be reduced to P. Complete decision problems are used in computational complexity to characterize complexity classes of decision problems. For example, the Boolean satisfiability problem is complete for the class NP of decision problems under polynomial time reducibility. Equivalence with function problems. A function problem consists of a partial function f. The informal problem is to compute the values of f on the inputs for which it is defined. Every function problem can be turned into a decision problem. The decision problem is just the graph of the associated function, such that f equals y. If this decision problem were effectively solvable, then the function problem would be as well. This reduction does not respect computational complexity, however. For example, it is possible for the graph of a function to be decidable in polynomial time, when the function is not computable in polynomial time. The function f equals 2x has this property. Every decision problem can be converted into the function problem of computing the characteristic function of the set associated to the decision problem. If this function is computable, then the associated decision problem is decidable. However, this reduction is more liberal than the standard reduction used in computational complexity. For example, the complexity of the characteristic functions of an NP-complete problem and its GO-NP-complete complement is exactly the same, even though the underlying decision problems may not be considered equivalent in some typical models of computation.